everyone. I'm Rachel Gordon, the Communications and Media Relations Officer at MIT's Computer Science and Artificial Intelligence Laboratory. Today, I'd like to give you a closer look inside the lab through the lens of our researchers. I'll now introduce Shashank Shrikant, the PhD candidate at CSAIL. His research interests are at the intersection of machine learning, program analysis, and cognitive neuroscience. Shash, tell me a little bit more about how studying the human brain when it reads code can help us better understand how AI can code for us.
Thank you for the introduction, Rachel. Hi, everyone. I'm Shashank, Shash, and I'm a graduate student at the Department of Computer Science here at MIT, where I'm advised by Dr. Unami O'Reilly, and I'm part of the Alpha Lab. My research interests are at the intersection of machine learning, program analysis, and cognitive neuroscience. And today I'd like to walk you through this fascinating world of programming languages and how cognitive neuroscience can help inform AI and to read and understand computer programs better. All right, so let's consider natural language, and let's consider this very conversation that we are having right now. I have certain ideas in my head, which are represented as thoughts, which I'd like to convey to you, the audience. And the way I go about it is we share a vocabulary, and I express these ideas in a vocabulary that you understand. I either write it down or I speak it out. And you, the audience who shares this vocabulary, reads it or listens to it and understands what this idea is that I'm trying to convey to you. So the communication game that we're playing between the two of us seems to be fairly well defined. From the ideas in my head as one audience, that is you, and the way I go about it is I articulate these ideas as words or as speech, and you, given that you share this vocabulary, understand what it is that I'm trying to convey. Fair enough. But let's see what happens in programming languages. Now, when I write a piece of program, I'm writing this in order to communicate certain ideas with my fellow programmers, because at the end of the day, someone else would also be reading this piece of code and trying to understand what it is that I'm trying to accomplish. So the communication game over here is happening between me and a fellow programmer trying to understand what it is that I'm trying to express. Now, that's just one side of the story. There's this other interesting side where I'm also expressing ideas in order to communicate and to a machine, in order for a machine to be able to understand what it is that I'm trying to achieve. So I write code down in order to convey to a machine what it is that I want to achieve, and the machine mechanistically just goes ahead and processes these instructions and computes the final output. Now, this is in stark contrast to how natural languages work, and that's what makes it extremely interesting. This whole notion of two actors being the audience of my communication when I'm writing programs has also been called the dual channel constraints in recent literature, and this is what makes programming languages a very interesting topic to study. And now add to this the task of teaching machines how to read code or how to understand code. Now, should we train these machines to also incorporate aspects which we write in order to communicate with our peers? Should we train the machines to also incorporate aspects which we use to communicate ideas to a machine? That's unclear as of now. And also, this relationship of how these two different actors influence how I express ideas is not well understood. So if I have to write a piece of program in order to optimally convey ideas to my peers, will that affect how a machine is able to understand programs? Or likewise, if I'm required to write this optimal piece of code which the machine can understand, does that necessarily mean my peers can understand what I've written? It's unclear. So that's what makes this problem so interesting. And in my attempt at understanding how we go about this exercise of understanding programs, I've taken two branches. One is a cognitive neuroscience approach, where we actually study humans and us, people, going about this process of understanding programs. So we identify what is happening in our brains, and we measure these quantities either through the time it takes us to react to certain kinds of inputs, or by directly measuring neural activities. And that gives us some representation for this entire cognitive task of understanding programs. Now, that's one side of the story. The other side is getting state of the art machine learning models to understand how these programs can be comprehended. So these machine learning models take in lots of programs as input, they're trained on it, and finally they come up with a representation of which is their understanding of what this program contains. And what's interesting is the bridge between these two worlds. Now, will these representations learned by machine learning models, will that provide us information which will help us improve how we as humans understand these programs? Or likewise, will an insight of how we understand programs improve how we can train machines? That's unclear, and that's pretty much the core of my work. Now, I'll give you an example of one piece of work that I did in this whole cognitive neuroscience space, where recently we tried to understand which parts of a brain are involved in reading computer programs. So we tested two parts or two systems of brain regions. One called the multiple demand system, which is usually invoked in tasks involving working memory, logic, math, general problem solving. And another system of brain regions called the language system, which is known to respond very strongly to natural languages. And the question that we were trying to ask and we were trying to investigate was, are programming languages really treated as languages by the brain, or is it something totally different? And what we did was we got a bunch of people and took them out into fMRI machines and observed the neural activity when they actually read computer pieces of computer programs. And what we found from and what we established, what we investigated in this work are we studied people reading two different programming languages. One is Python, which is a popular programming language which people use these days, and another is Scratch Junior, which is a completely visual programming languages. It doesn't have any words in it, and that became like a nice experimental control to study the effect of text in programs. So was the activity that we were seeing, could that be explained just by the words and the letters present in programs? We wanted to control for that. And hence Scratch Junior is like a perfect candidate for it. And what we ended up finding was the language center is not consistently activated when reading computer programs, whereas the multiple demand system is, which is an interesting result in itself. So this is where we are, and this is pretty much the tip of the iceberg. So it'll be interesting to see how this knowledge can improve the way in which we train these machine learning models in order to read and comprehend computer programs. That's pretty much what I had. So feel free to write me an email, find me on Twitter. I'll be more than happy to engage with you on this fascinating topic. Thank you so much.
Thanks so much, Shash. That was fascinating. So I want to ask you a few more questions about this project. First off, what inspired you to borrow tools from cognitive psychology and neuroimaging to better understand how we read computer code?
Yeah, that's an interesting question. So if we take a look at the history of how some of these fields have developed, one thing that stands out common in all these attempts is they all have their roots in cognitive neuroscience and in observing how we ourselves go through these different processes. For instance, if you take at vision and research in vision, before computational models were developed to explain how we could probably go ahead and recognize images and identify what's in an image, scientists first started off with understanding how it is that we humans go about it. Can we figure out whether there are some things in common or there are some idiosyncratic patterns in which we are able to identify images or not identify images? It's the careful study of our own behavior which inspired lots and lots of the computational models which help explain these behaviors today. And unfortunately, and this has been the case with vision, language, most of the cognitive senses that we have. And unfortunately, the study of programming languages has not seen the same treatment. So I thought, yeah, why not? This is like a good first step to start things off.
Mhm. Now, your research suggests that there isn't a definitive answer to whether coding should be taught as a language or a math-based skill. Why is
Uh-huh.
that?
Yeah, so there's a lot to unpack in that question over there. So the work that we have actually investigated is people reading computer programs. So programming as an activity itself has like multiple dimensions to it. One could think of like problem solving as a part of programming, writing programs as a part of programming, understanding someone else's program as part of programming, debugging code as part of programming. So it has all these different dimensions, and we studied one dimension, which is just reading and understanding and comprehending programs. And even in this one small activity, what we did notice was the language system is not recruited consistently, whereas the multiple demand system is. But that definitely does not mean that the language system has no role in it. One ideal way to test that would be to snip a person's language system off and then study what the behavior is. And unfortunately, we don't have any such results so far. So it's not very clear whether uh, one should rule out the language system's involvement completely. It's just that what we find is the multiple demand system seems to supersede the language system's role in understanding these programs. But as I said, I mean, it's an open question, and we need more investigations into the exact role and the exact nature of these two systems or any other systems in the brain.
Yeah. And then besides programming, what other types of tasks are associated with the multiple demand network?
Yeah, so the multiple demand network or the system of brain regions is a very interesting, fascinating brain system. So, over the last 20 years, what research in neuroscience has informed us is there are very specific parts of the brain involved in very specific cognitive activities. And we didn't know of the existence of these regions until like 10 or 15 or 20 years ago. So, for instance, we've got regions in our brain which specialize to something like just recognizing faces or understanding locations or reaching out to objects or grasping objects. All these activities, these specific activities, have one specific region or their corresponding specific regions in the brain controlling and responsible for it. Now, this multiple demand system is a complete antithesis to this paradigm, where it seems to activate in a host of general problem-solving tasks. So, for instance, if there's any task that we seem to have encountered for the first time and we are trying to figure it out, that's when the multiple demand network kicks in. So usually it's seen in tasks involving working memory, in logic, in math, in any kind of problem solving, including even probably learning a second language. So these are some of these tasks where the multiple demand network activates and is seen to participate.
Mhm. I want to shift now to talk about AI. Can you
Mhm.
talk more about how research in cognitive psychology can help us better design AI models for code?
Yeah, so that's again like a very fascinating area, and the intersection is like a, quite fascinating, and I just touched upon it in my slides. Again, going back to very recent work, and this is work done at MIT across the street over at the Department of Brain and Cognitive Sciences, where they've showed that computational models which learn how to recognize images, if we dissect and look at the layers of those models, we seem to find exactly those patterns which our brains or the different layers of our brains figures out. So that's something very interesting and very non-obvious. So if we know that, let's say, the human brain processes images in stages. And when we look at an image, we first try to understand the edges, we process the edges, and keep growing in the complexity of like the kinds of information we can discern from a given piece of image. And what they've shown is there's this direct correspondence in computation models as well, which are trained to understand images. And what's fascinating is if there is such a correspondence in programming languages as well. So, for instance, how we comprehend programming languages versus how computational models learn programming languages. It's very interesting that probably we could use information from one to inform the other. So, for instance, if a computational model ends up discovering some idiosyncratic pattern like loops or recursion, which is something very specific to programming. It is probably then quite possible that these kinds of structures or these kinds of information are also available in and stored in different parts of our brain. And likewise, if we manage to figure the brain puzzle out, maybe that should help us train these computational models better. So yeah, it's a fascinating area, and we're just beginning to touch on the complexities involved in understanding this and understanding how both of them can be studied together. And that's what makes this problem all the more exciting.
Wow, that's incredible. Okay, I want to interject with an audience question from Matthew.
Sure.
Have you employed AI or machine learning in edge computing or in other decentralized networks? If so, what challenges did you encounter in implementing AI in edge computing that did not exist in central or larger locations?
So no, unfortunately, edge computing is something that is beyond my specific research interests. So I haven't really dabbled with AI/ML in edge computing. So yeah, unfortunately, I don't have a good answer to this.
Now, given how we're progressing towards more sophisticated machine learning models, what would you tell people who are worried that AI is going to replace programmers in the near future?
Yeah, so probably my job is also on the line over here. So jokes aside, I think we're quite a far way away from that happening. And the reason why I think so is because programming, as I mentioned, involves these different dimensions of tasks. All of them are fairly non-trivial. So we as humans ourselves seem to quite struggle with mastering each of these different components. And given where we are with the state of the art in training machine learning models to perform such tasks, I don't think we're there yet. But however, I think what's also interesting is to acknowledge and realize that the whole enterprise of programming and all the related activities involved, there exist a number of components which are very rote, very routine, and uh, which requires a lot of attention to be given to those specific small details, which can be automated. So, to be quite pragmatic, what I do see is the role of AI helping or improving program productivity than actually replacing it. So there are these number of tools that can be thought of, which can completely make a programmer's life very easy as compared to what they have to deal with right now. For instance, think of like Google search. When we go ahead and write out a little query, it auto completes and just takes away those 5 seconds of time that we would have otherwise spent in like making a spelling correction and mistake and figuring out what it is that we wanted to convey. Similar such tools can be thought of for programming languages as well. And it's interesting how machine learning and AI seem to be perfectly placed to intervene and provide such solutions to us.
The autocomplete always gets me. They have the most hilarious suggestions. And I'm like, who is searching for this? Because it's not me.
Absolutely.
So I have another audience question here
Sure.
from Emily. Have certain injuries or disabilities been studied in the programming comprehension context? And she didn't specify what, but I would assume possibly neurodegenerative disorders or CTE or anything within that realm.
That's such an interesting question, and this is probably only being studied now. I know a group over at MGH, which is Mass General Hospital, where some of these studies are being thought of. So just to provide some more detail, in fact, one can think of studying patients or people with aphasia. So aphasia is this neural condition where the language system is affected. So people usually do have the right ideas in their heads, but then aren't able to generate speech or generate language in order to express those ideas. So what would be very interesting is to investigate whether their ability to read programs are also impeded, given that their language system has been affected because of this neurological condition. So it's a great question, and I wish I had more answers, but I think that's where the field needs to venture into to understand how it is that we go about this activity and what are the neural or the cognitive bases of reading and understanding programs. So yeah, great question. Yeah.
Definitely. And I imagine there would need to be kind of a lot of large scale tests to obtain something like this.
Absolutely. Absolutely.
Yeah. So how can this work and what you've studied in your research influence how we teach coding to future generations?
Yeah, so teaching is, again, a big application of works like these. And again, let me clarify that teaching programming also involves all these different dimensions that I've just mentioned. But if we have to even focus on teaching oneself to improve one's ability to read and comprehend programs, which seems to be related to the kind of work that we've done, the answer, unfortunately, is not clear and is much more complex than what meets the eye. So if one has to really understand how, so the crux of our result, the research result is that reading computer programs also activates the multiple demand network, which seems to be involved in all these tasks like math and logic and working memory. Now, there have been some works in the past which have claimed that in order to improve oneself, so if there are two tasks which share the same brain region, so in our case, it is programming language and let's say logic, and they share this multiple demand network. So what recent works have claimed is that training yourself on one task helps improve your ability to your performance in the other task. So for instance, if I focus and train myself on improving my logic skills, which is where the multiple demand system is involved in, seemingly it should help improve my ability to read and comprehend programs as well. So the tools used to understand one task transfers onto the other task which shares the same brain region. Now, there aren't a lot of works which have studied this in great detail. There are just a few works that have come out over the last couple of years, and it's quite a contentious issue. There are results and counter results, and the field is undecided whether this is actually true. And specifically in the case of programming languages, we just don't know. Unfortunately, this work hasn't been studied. So I guess this is a potential research question for me myself to go ahead and explore. So, yeah, I would love to give like a nice little template answer saying, okay, this is what you need to do to improve yourself, to improve your coding abilities. But unfortunately, we're not there yet. These studies are not mature enough to inform those kinds of applications.
But I really appreciate how this could set a precedent for a framework to better understand how we teach other topics as well, and kind of get rid of our one-size-all approach to topics such as math and science and reading, and better understanding the different regions of our brains and how they work in different ways than the person sitting next to you.
Absolutely, and that is such an important point because our brains are all designed in very different ways, and we all have our own space, the pace at which we learn and understand things. And the role of cognitive psychology, unfortunately, is underplayed when it comes to these very important applications, such as teaching these topics. So yeah, that's a great point.
Right. And I think as we continue to understand the brain and all of its layers, we will be able to use your framework to help educate all of the coders and learners of the future.
Hopefully, I mean that's the aim that I wish for. I mean that's if that happens, nothing like it, I suppose.
Definitely. Well, thank you so much, Josh, for speaking with us today, and thank you everyone for coming to this MIT Inside Track.
It's my absolute pleasure. Thank you so much, Rachel.